Imagine staring into a mirror that doesn't just reflect light, but time itself, peering not at your own face, but into the infancy of the universe, when existence was still wrapping itself around its first breath. That's precisely what the James Webb Space Telescope was built to do. But what it found when it looked deeper than anything before it was an infancy. It wasn't the cosmic cradle. It was a contradiction, a cosmic impossibility. And what it saw, what it revealed to us, has not just stunned astronomers. It has shaken the very skeleton of modern physics. First glimpse of galaxies far, far away as NASA's new Webb telescope releases its first images from the deep universe. Now, galaxies that are far, far away have gotten a little bit closer. Yeah, there are dazzling images from the James Webb Space Telescope that were recently unveiled. When the James Webb Space Telescope turned its eye to a distant, seemingly quiet corner of the cosmos, no one anticipated the extraordinary discovery that would follow. Trained on a galaxy more than 13 billion light-years away, just a few hundred million years after the Big Bang, Webb's powerful infrared sensors picked up something that defied all conventional understanding of early cosmic evolution. The telescope didn't just detect light from ancient stars or the signature of young galaxies forming. It captured what appears to be the structural complexity of a fully developed galaxy, complete with intricate spiral arms and a supermassive black hole at its core. Before we start, smash the like and subscribe buttons for more updates. This was unimaginable. According to current cosmological models, such complexity shouldn't exist that early in the universe's timeline. The cosmic clock had barely started ticking. And yet there, frozen in time and light, was a galaxy behaving like one that should be billions of years older. It wasn't just the presence of stars or black holes. Those could theoretically form quickly. It was the entire structure of the galaxy, which indicated a level of gravitational organization and stellar evolution that should have taken much longer to achieve. The James Webb Space Telescope, with its unprecedented resolution and deep field capabilities, is built to peer further into the past than any instrument before it. Unlike Hubble, which primarily observes in visible and ultraviolet light, Webb operates in the infrared spectrum. This allows it to penetrate clouds of cosmic dust and view the faint redshifted light of some of the universe's first galaxies. What it found this time pushed the boundaries of cosmic archaeology. A high redshift object not only massive in scale, but exhibiting elements of galactic maturity that simply shouldn't be possible within 300 to 400 million years of the Big Bang. Spectroscopic analysis revealed staggering details. The light emitted from the galaxy, although stretched and diluted by time and space, carried the fingerprints of heavier elements, carbon, oxygen, and even traces of iron. This alone was stunning. Heavy elements are forged in the hearts of stars and released into the cosmos through supernova explosions. Their presence here meant that multiple generations of stars had already lived and died in rapid succession. In cosmic terms, this is akin to watching an infant suddenly leap into adulthood with no transitional stage. Such an evolutionary leap couldn't be explained by current models of star formation and nucleosynthesis. Even more shocking was the central concentration of mass. At the heart of the galaxy sat a supermassive black hole estimated to be over 1 billion solar masses. For context, even the most aggressive formation models, those accounting for runaway growth and super Eddington accretion rates, don't predict black holes of this size forming in such a short time frame. The prevailing theories assumed that black holes began as remnants of population 3 stars, growing slowly over billions of years through mergers and accretion. Yet, here was one that seemed to have skipped several steps, appearing fully formed in the blink of cosmological time. The implications rippled through the scientific community almost immediately. Either our understanding of early star formation was drastically flawed, or there existed mechanisms of matter organization and black hole formation that had been entirely overlooked. One idea floated was that dark matter, an invisible form of matter that makes up most of the universe's mass, might have played a more active role in shaping early galactic structure. Perhaps dark matter clumps provided the gravitational scaffolding necessary to accelerate the birth of these colossal systems. If true, this would redefine dark matter not just as a passive background force, but as a dynamic architect in the universe's early blueprint. Another possibility was that the initial conditions of the universe were far more volatile and creative than previously believed. The chaotic density fluctuations shortly after the Big Bang may have given rise to ultra-efficient starburst regions, galactic nurseries that churned out stars at rates never before imagined. These regions could have led to rapid chemical enrichment and supermassive black hole seeds forming almost instantaneously. But even these revised ideas struggled to fully account for the scale and maturity observed. Webb's detection didn't stop with one anomalous galaxy. Follow-up observations uncovered multiple such candidates scattered across different sectors of the sky. This suggested the phenomenon wasn't an isolated case, but possibly a widespread phase in early cosmic history. The universe, it seemed, was far more eager and capable in its youth than anyone had expected. Entire galactic systems, replete with dense stellar populations and complex structures, were emerging in epochs previously thought to be ruled by primordial chaos and simplicity. Gravitational lensing provided a crucial assist in confirming these findings. In several cases, the light from these early galaxies was bent and magnified by massive intervening galaxy clusters, acting like a natural telescope and giving astronomers a clearer view. The clarity revealed in these lensed images was hauntingly beautiful. Nebular tendrils, rotational arms, and evidence of dust lanes, features thought to be hallmarks of galaxies that formed much later in cosmic history. Yet here they were, gleaming with ancient light, stretching back almost to the beginning of time itself. Some theorists began revisiting the inflationary model of the universe, pondering whether the initial expansion may have seeded the cosmos with more complex matter distributions than previously calculated. Could there have been pockets of space-time where conditions were uniquely favorable to rapid matter organization? Was the Big Bang less uniform than the cosmic microwave background led us to believe? Webb's revelations hinted that the early universe may have had much more nuance, structure, and even intentionality baked into its chaotic origin. Compounding the mystery was the detection of molecular signatures within some of these galaxies, signatures indicating the presence of water vapor, carbon dioxide, and even organic precursors. Though these molecules can form in interstellar space through natural processes, their presence in such ancient galaxies suggested a level of chemical sophistication that was not anticipated. These weren't sterile pockets of dust and gas. They were environments already exhibiting the potential ingredients for complexity, possibly even life, in the universe's earliest chapters. Webb's instruments also detected peculiar fluctuations in the background light around these galaxies. These were not gravitational lensing effects, nor were they consistent with known cosmic microwave background anomalies. Some scientists speculated that they could be due to gravitational waves produced by dense early galactic mergers or exotic objects like primordial black holes colliding. If confirmed, it would provide the first electromagnetic evidence of gravitational wave phenomena from the early universe, opening a new channel of exploration into cosmic origins. While traditional interpretations struggled to keep pace, new models began to emerge. One proposed that perhaps we had misunderstood time itself. What if, in the early universe, time flowed differently under extreme gravitational and energy conditions? Under such a framework, processes that appear instantaneous to us might have unfolded over much longer durations locally, hidden behind relativistic effects. While highly speculative, such theories sparked debate across cosmology, quantum mechanics, and even the philosophy of time. The James Webb Space Telescope was designed to answer big questions about the origins of stars, galaxies, and ultimately the universe. Instead, it has raised even bigger ones. The detection of fully formed galaxies and supermassive black holes at redshifts previously considered impossibly high has sent theorists scrambling for revisions. It's not just about discovering older things. It's about uncovering an entirely new behavior of the universe in its infancy, one that seems to contradict the very scaffolding of modern cosmology. What Webb has glimpsed is nothing short of a cosmic enigma. The telescope has turned its gold-plated mirrors toward the most ancient light and found not the expected seeds of structure, but mature systems flourishing against all odds. It's like discovering skyscrapers in the ruins of what was thought to be a barely settled frontier town. It challenges the very narrative of how the universe matured, forcing a reconsideration of everything from stellar life, cycle timing, to the behavior of dark matter and the influence of unknown forces in early spacetime. What makes this discovery even more profound is its scale. We're not talking about one anomaly, one rare exception. The number of early massive galaxies that Webb has identified so far implies that the phenomenon is not marginal. It's potentially fundamental. The early universe wasn't just chaotic and primitive. It may have been astonishingly productive. This shifts the goalpost for what astronomers should expect to find when they peer deeper into space and further back in time. Webb's detection also opens new doors in the search for the origins of life. If complex chemistry was already taking root this early, it raises the possibility that life-friendly conditions could have emerged not billions, but hundreds of millions of years after the Big Bang. It redefines what early means in cosmic terms and injects new urgency into the search for biosignatures in ancient exoplanet atmospheres. If the building blocks were already in place so soon, then perhaps the emergence of life is not the improbable miracle it was once thought to be, but rather a natural consequence of a hyper-efficient universe. Instruments like NIR-SPEC and MIRI have become cosmic time machines, translating faint whispers of ancient starlight into data that speaks volumes about how little we truly understand. Every photon captured by Webb seems to challenge a previously accepted truth. With each new dataset, the telescope is not just seeing further, it is revealing a universe that's deeper, richer, and stranger than any theory had dared predict. It's easy to forget that light takes time to travel. When Webb sees a galaxy from 13 billion years ago, it's not just looking at distance, it's gazing into time itself. What it sees now, we never could have imagined. The early universe, once thought to be a murky soup of gas and darkness, appears to have been a bustling workshop of matter, form, and potentially even precursors of life. In that ancient light lies a message we are only just beginning to decode, and its implications may echo through the corridors of science for decades to come. The James Webb Space Telescope has not just detected the unimaginable. It has ignited a firestorm of discovery that will reshape how humanity understands the cosmos. Every time it peers into the void, it seems to find something even more astounding. And yet, this might just be the beginning. As James Webb continues to probe the depths of cosmic history, its latest revelations show not only physical structures that baffle the scientific community, but patterns of motion and energetic behaviors previously unobserved. In one instance, a galaxy situated at an extraordinary redshift was found to exhibit rotational dynamics more consistent with mature galaxies in the current epoch than with any model of the early universe. This wasn't just a rough, loosely bound cloud of stars. It was a structured rotating disk exhibiting a velocity gradient that indicated established gravitational equilibrium. How could such a system have organized itself with such coherence in the blink of cosmological time? The rotation curve of this galaxy, essentially a graph of how fast stars and gas move at different distances from the center, was unexpectedly flat. This phenomenon, well documented in modern galaxies and typically explained by invoking dark matter halos, suggested that such dark matter structures may have formed even earlier and more robustly than previously believed. But this leads to another conundrum. If dark matter halos were this mature this early, they must have undergone gravitational collapse and stabilization in record time. The implications force theorists to ask if dark matter is not only more prevalent, but perhaps more interactive in early epochs than expected. We knew about the beginning is wrong. When the Webb telescope first captured the image of what now seems to be an impossibly mature galaxy, sitting over 13 billion light-years away, it was expected to be another faint ancient smear of light barely distinguishable from background noise. But instead, what stared back was nothing short of architectural elegance. Spiral arms wrapped like ribbons of starlight, dense star clusters orbiting in harmony, and a dense core pulsing with energy. This galaxy wasn't forming. It was formed, and not just barely. It looked like something we'd expect to find several billion years into the universe's timeline, not within the first few 100 million years after the Big Bang. To understand why this is so baffling, you have to understand how galaxies are thought to evolve. In the early universe, matter was spread thin and uneven, gradually pulled together by gravity into clouds that collapsed into stars, which then grouped into galaxies over enormous time frames. But what Webb saw suggested that this entire process had already completed far too quickly. That galaxy hadn't just taken shape, it had thrived. The laws of astrophysics didn't allow this. It was like finding a fully grown ancient redwood tree sprouting from freshly planted soil. Even more puzzling was that this wasn't an isolated phenomenon. Webb uncovered multiple examples. Galaxies across different regions of the sky, all displaying levels of organization, complexity, and maturity that were flat out impossible according to our current understanding of cosmic timelines. And this wasn't just a glitch in the telescope. The instruments were working perfectly. What wasn't working was the framework of our theories. Once astronomers analyzed the spectral data, the fingerprint of light that reveals the elements within these galaxies, they were hit with another shock wave. Not only did these galaxies exist, but they contained the chemical signatures of elements that shouldn't have been there yet. Oxygen, carbon, even iron. These elements don't come from nowhere. They're forged in the hearts of massive stars and only released into the cosmos through supernova explosions. That process takes time. First-generation stars called population 3 stars burn hydrogen and helium. Then they die, scatter their contents, and eventually second-generation stars are born enriched with heavier elements. That entire sequence should have taken hundreds of millions, if not billions of years. But here they were, galaxies less than 400 million years old, showing signs of multiple generations of stellar death and rebirth. That would mean that not only had the first stars formed and died, but that the cycle had already repeated more than once. The early universe, it seems, wasn't quietly waking up. It was sprinting, forging, burning, and exploding in ways no one anticipated. And the presence of these elements raises even deeper questions. Because these are not just the ingredients for stars. They are the foundation for planets, atmospheres, and potentially life. To find them so early is like stumbling across a thriving coral reef at the base of a volcano that only erupted yesterday. The timelines don't just feel rushed, they feel broken. Just when scientists thought things couldn't get more confounding, the center of one of these ancient galaxies delivered the most outrageous surprise of all. Nestled deep within its core was a supermassive black hole estimated to weigh over 1 billion times the mass of our Sun. In today's universe, that would be incredible. But in the early universe, that's not just unlikely, it's cosmologically absurd. You see, black holes are thought to grow gradually. They begin as the remnants of massive stars, then feed over billions of years by consuming gas, dust, and other stars. Even the most optimistic simulations with accelerated growth models and nonstop feeding can't explain how such a colossal black hole could form within 400 million years of the Big Bang. It would be like finding a fully grown adult who was born just an hour ago. The math doesn't work. And yet, there it was. The gravitational signature was unmistakable. The rotation of nearby stars, the energetic emissions, the warped space around it. Everything pointed to a black hole that had skipped adolescence entirely. It didn't grow. It arrived. Scientists are now entertaining radical theories. Primordial black holes formed directly from the collapse of extreme density fluctuations in the early universe, or perhaps the influence of exotic particles or dark matter accelerating their growth. But these are not adjustments to current models. These are completely new blueprints for reality. What do you do when every observation defies the rules you've been taught? For many cosmologists, the answer is unsettling. You rewrite the rules. Because the James Webb Telescope hasn't just shown us anomalies. It's revealed a universe that seems to be behaving in reverse, where complexity comes before simplicity, and where ancient light carries blueprints that shouldn't exist. Some scientists now propose that dark matter, long thought to be a passive gravitational force, might have played a more aggressive role in shaping the early universe, forming scaffolds that fast-tracked galaxy growth. Others suggest that time itself may have flowed differently in those early moments, stretched and warped in ways we can't yet detect, allowing entire epochs of evolution to pass in what appears to us as mere flashes. And then there's the most chilling idea of all, that perhaps the early universe wasn't so different from the one we see today. Maybe complexity is not the end point of cosmic evolution. Maybe it's the beginning. As the data kept flowing, researchers began to notice something even stranger. Something that had nothing to do with the brightness or the mass of these galaxies, but with the shapes they repeated. Using deep learning algorithms, scientists found that the distribution of these ancient galaxies followed a very particular repeating mathematical ratio, one eerily similar to the golden spiral. This was not just aesthetic. It was structure, a hidden geometry that spanned billions of light years, linking star systems and galaxies in elegant alignment. The very layout of matter seemed to follow a fractal logic, as if the universe was coded from the beginning with a design that echoed across scales. It wasn't just coincidence. The spiral arms, the rotational symmetry, the orbital distances. Webb's high-resolution imaging revealed that what we thought was random chaos in the early cosmos may in fact have been patterned, predictable, like fingerprints. But fingerprints of what? A fundamental law deeper than physics? Or something far more disturbing? Evidence of intentionality embedded into space-time itself? One of Webb's most controversial findings came not from a galaxy or a black hole, but from the faint chemical trail left behind in a seemingly empty region of space, an interstellar void so ancient it was assumed to be sterile. But the telescope's spectrometers detected something inexplicable: complex organic molecules, not simple methane or ammonia, but polycyclic aromatic hydrocarbons, the building blocks of amino acids, and by extension, life. These chemicals weren't attached to planets. They weren't swirling inside stars. They were drifting, aimless, and yet somehow intact after 13 billion years. This raised alarms because the implications were beyond biological. It meant that the ingredients of life had existed nearly since the beginning, not formed later in solar systems like ours, but seeded into the fabric of the cosmos almost immediately. And if that's true, then life isn't a fluke of planetary alignment. It's a feature, a constant, a thread woven through the universe from the start. The unimaginable, it seems, wasn't just galactic. It was molecular. Then came the image that threw even the most skeptical minds into silence. Deep within a cluster of high redshift galaxies, Webb detected a formation that was too perfect. 6 galaxies positioned like petals around a central object, spaced at equal distances, rotating in near synchronized orbits, like some cosmic dance choreographed with a purpose. Scientists called it the flower. And despite their efforts to explain it away as a statistical anomaly or gravitational coincidence, no natural model could reproduce its precision. It was an astronomical sculpture frozen in light from a time before Earth had formed. Some proposed gravitational lensing. Others suggested quantum symmetry left over from early universe turbulence. But a quiet few wondered aloud whether this might be something else entirely. A marker, a signpost, a calling card left in plain sight, meant only to be seen once humanity's eyes had evolved enough to perceive it. And finally, the most chilling theory to emerge from all of this, that the very act of observing these ancient galaxies might be influencing them retroactively. Known as the observer effect in quantum physics, it describes how the outcome of an event can be altered simply by being measured. But what if this principle doesn't stop at particles? What if the universe, on some unfathomable level, is responsive to attention? That by building James Webb and peering into the early cosmos with this unprecedented clarity, we didn't just uncover secrets. We woke something up. This theory, once laughed off as philosophical noise, is now being taken seriously by a fringe of physicists who see patterns in the Webb data that shift depending on how and when they are processed. Some images seem to alter subtly over time, as if the universe itself is reacting to being observed. If true, it would mean we're not just explorers. We're participants, co-authors of the very reality we seek to understand. What the James Webb Space Telescope detected was never just about stars or black holes or dust drifting through time. It was about truth, a truth so vast, so ancient, and so intricately woven into the fabric of everything that to witness it is to feel the scaffolding of reality tremble beneath your feet. We didn't just see the unimaginable. We unlocked it, not by force, but by attention, by daring to ask questions no civilization before us had the technology or the audacity to pose. Galaxies too mature, chemistry too complex, patterns too perfect, signals too aware. What Webb revealed is not simply that the universe is more mysterious than we imagined, but that it may be aware of our imagination. That perhaps for the first time in history, the cosmos whispered back, not in words, but in light, in formation, in echoes that bend across time itself. Maybe we didn't find the edge of the universe. Maybe we found its memory, and it remembered us. So now the question isn't what did Webb see? The real question is what saw Webb? If this left you shaken, if the patterns felt too sharp, the timing too perfect, the revelations too synchronized to be random, then you're not alone. Subscribe because we're not just watching the stars. We're watching the response. Turn on notifications because the next signal may already be incoming. Share this video with someone who still believes the universe is silent. Comment below. What do you think Webb saw or woke up?